Rocking around the Christmas tree, let the Christmas spirit ring. Do, do, do. Later we'll have some pumpkin pie and we'll do some caroling. What is that? Rocking around the Christmas tree, have a happy holiday. Do-do-do-do-do. Seriously, what do you think that is? Everyone dancing merrily in a new old-fashioned way. I don't know, but it's cute pom-pom. Boom. Hello and welcome to another Math Monday, you guys. Merry Christmas, happy holidays. We're almost there and I'm so excited. And so today, as a gift for you, I'm gonna help you unravel all the secrets, or well, let's face it, some of the secrets to Pascal's triangle. All right, so I know your first question must be, what is Pascal's triangle? And oh my goodness, I'm so glad you asked because I'm so ready to tell you. Pascal's triangle is this super magical thing with this beautiful pattern. So first of all, every row has to start and end with 1. Each term in the triangle is the sum of the 2 terms above it. Okay, so we start with just 1 and then 2 ones on the other end. So what you can also do is, if you really want to, envision some invisible zeros around the triangle as well. So you could have 0 plus 1 is equal to 1 and 0 plus 1 is equal to 1. But if you just know to start with 1s, then there you go. And then the third row would be 1, 2, 1. Fourth row is 1, 3, 3, 1. So technically I just said something wrong there because the first row is actually row 0, which I know, but you'll see why. Just trust me. So the first row is row 0. The second row with the 1, 1 in it, that's actually row 1. The 1, 2, 1 is row 2. The 1, 3, 3, 1 is row 3. So really, what happens is every single row, so the nth row has actually n plus 1 terms in it. So the third row has 4 terms in it. The fourth row has 5 terms in it. The sixth row has 7 terms in it. You guys get it, okay? So this is Pascal's triangle. It can actually go on forever and ever and ever, but here's the first little bit of loveliness for you. So this beautiful triangle here that I drew up, kind of looks like something else. It can go on forever and ever. It is infinitely big, which is why it's full of secrets. If you just got that joke, we just became best friends. So let's unlock some of these secrets of Pascal's triangle. So the first one I want to unlock, let's try taking the sum of each row. So the sum of 1 is 1. Sum of 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 1 plus 4 plus 6 plus 4 plus 1, well, if you like 4 and 6 is 10, plus another 4 is 14, plus the 2 is 16. 1 plus 5 plus 10 plus 10 plus 5 plus 1, well, 10 and 10 is 20. 5 and 5 is 10, so that's 30, and 2 more is 32. And then 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, 20 and 15 is 30, so that's 50 plus 12, the 2 6s is 62 plus the 2s is 64. I'm going to stop there because I think you get the point. Let's look at those numbers. 1, 2, 4, 8, 16, 32, 64. Do you see it yet? Those are all powers of 2. Meaning 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 to the power of 3, 16 is 2 to the power of 4, 32 is 2 to the power of 5, 64 is 2 to the power of 6, it keeps going. So that's something that's kind of crazy if you think about it. The sum of all the rows is 2 to the power of n, where n is the row number. So we can use some technical mathematical mumbo jumbo to represent this, and that is the sum of n choose k from k equals 0 to n is equal to 2 to the power of n. Which takes me to my next secret about Pascal's triangle that's actually pretty interesting. Before I do that, I just want to remind you a little bit about combinations. I did a few videos on that eons ago. Please go look for them. But a combination is something where we say this n over k in the brackets, and that's pronounced n choose k. And what that is equal to is n factorial over k factorial times n minus k factorial. Okay, let's just do an example really quick. So say I have 5 choose 3. Well, that's going to be 5 factorial because it's in the place of n, over 3 factorial times 5 minus 3 factorial, which is 5 factorial over 3 factorial times 2 factorial. So remember, how to find a factorial is multiply that number by every number lower than it until you get to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1, and 2 factorial is 2 times 1. So here I can cross out the 3 times 2 times 1 on both the top and bottom. So 5 times 4, I'm left with 20, and 2 times 1 on the bottom, I'm left with 2. So 20 divided by 2, and that is 10. Oh, interesting. If we go back to our Pascal's triangle from before, that's actually the third position of the fifth row. Now, that's really important to note, though, that each row starts with a 0 position, and we know that our row numbers start with a 0 as well. So really, to like sane people, it would actually look like the 6th row and 4th position, but we're starting with zeros here. So it's actually the 5th row and 3rd position. So this is another property of Pascal's triangle. Each number in the succeeding rows is actually a combination of the row and position number. So our first row is 0 in the 0 position, so that's 0, choose 0, which is 1. There's only one way to choose nothing. If you have nothing, you just don't do anything at all. And then the next row is the first row, so we can choose 0 or 1 things. We have the second row, you can choose 0, 1, or 2 things. The third row, you can choose 0, 1, 2, or 3 things. The fourth row, you can choose 0, 1, 2, 3, or 4 things. And the fifth row, of course, you can choose 0, 1, 2, 3, 4, and 5 things. So we see that 5 choose 3 right there was actually the 10 in the Pascal's triangle. So here we go, yet another property of Pascal's triangle, where each row is a combination n choose k, where n is the row number and k is the position. Just remember that n and k both starts with zeros and not 1, because why would we want to make anything too easy in math? All right, the next secret on our journey through Pascal's triangle is that each row is really just an expression of the coefficients of x plus 1 to the power of n, where n again is the row number. So for example, the first row is the 0th row, so that's 1, so x plus 1 to the power of 0, yeah, that's 1. The next row, row 1, is x plus 1 to the power of 1, so that's 1x plus 1. The next row, 1, 2, 1, so that'd be 1x squared plus 2x plus 1. Next row is the power of 3, so we have 1x cubed plus 3x squared plus 3x plus 1. This is actually the answers to x plus 1 to the power of n. So I can keep going for rows and rows and rows, and this will always get me the coefficients. So therefore, if you do ever need to take x plus 1 to the power of 5, you don't have to actually multiply x plus 1 out 5 times. Guess what? You can just use Pascal's triangle, get to the 5th row, and know all the coefficients, and then just know that the powers of x go from the n, or the row number, down. So this actually also works for x minus 1 to the power of n. Just know that you have to alternate adding and subtracting, starting with adding between the first 2 terms, and then go subtracting, and then add, and then subtract, and then add, and then subtract. All right, the next secret I want to take a look at is that each diagonal row gives a different set of numbers, which is pretty cool. So obviously the first diagonal row is just all the ones, so let's just draw those. Those aren't that important. Then the second diagonal row is actually all my natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. The third diagonal row down is 1, 3, 6, 10, 15, 21, 28, 36, so on and so forth. These are actually what we call triangular numbers because we need this many circles to always make a triangle. So if you have 3 circles, you could have 2 in the bottom, 1 up there. If you have 6 circles, you have 3 in the bottom, 2, and then 1. If you have 10, then you have 4, 3, 2, 1. You get what I'm saying. So those are what triangular numbers are. Then the next diagonal row down, 1, 4, 10, 20, 35, 56, 84, so on and so forth. This is what we call tetrahedral numbers. And so this is similar to the triangular numbers, but instead of being able to make a perfect triangle with each number, we can actually make a perfect tetrahedron. So what is a tetrahedron? It's basically a 3-dimensional triangle. So there's 4 triangular faces, and they all have the same triangle on their face, and it's an equilateral triangle everywhere. So this makes yet another very pretty looking pattern. I'm just gonna put that round thing down there. Why do I keep doing that? It seems kind of weird. All right, and the last and really the most fun secret that I'm going to share with you guys. By the way, this is by no means the last secret about Pascal's triangle that exists. There's so many patterns that we can find in Pascal's triangle. It's actually insane. All right, so for this interesting property of Pascal's triangle, I'm gonna color all the even numbers one color and all the odd numbers another color. I'm just gonna go ahead and happen to choose green for odd numbers and red for even numbers, just because, you know, I feel like it. So if I fill in all the odd numbers as green and all the even numbers as red, I get this beautiful looking thing. It's practically a piece of art. It actually is a piece of art. It's a fractal. What's a fractal? Well, a fractal is just a never-ending, infinitely complex pattern that's self-similar across different scales. I mean, obviously, right? So if I really want to get into what a fractal is, I'm pretty sure that's a whole other video, but it's basically a pattern that just keeps repeating itself. You can get infinitely small and infinitely big. You can keep building on top of it, or you can keep shrinking it in. And that's what this makes. This is a very special fractal pattern, but it's also just pretty, where we have these upside down triangles that just keep repeating themselves within here, and they can get bigger and smaller and bigger and smaller and bigger and smaller. So hopefully you've been realizing this entire time that I've been making Christmas trees. Okay, so I'm kind of holding on to the whole Christmas theme by a thread here. But let's face it, what a great excuse to make a bunch of Christmas tree looking mathematical crafts. If you have a kid who's working on adding and sums, you should do this with them. Make different things, different colors, make different patterns out of them. It's pretty fun. I know I have a nephew that is in love with math and science, and I'm going to be bringing this home to him this Christmas to make some fractal trees. Well, that's it for me today, you guys. A very happy holidays to you. Thank you so much for watching. Merry Christmas to all, and to all a good night.